the neuromorphic or the semiconductor, right? Today I talked to another student, we were saying, oh, it was very amazing. Nowadays, even if we see COVID-19, the electronics is the one that is still growing, right? 20 years ago, the visiting scholar in my school told me that you should quit semiconductor. This is the end already. But no, but today we are still talking about semiconductor. It just have different content. Of course, we are not saying that we are still doing this transistor, but we are doing something new for a new system, new circuit, right? It just keep going. Now it's AI. We don't know what happened next, maybe 6G or someone come up with something new, right? Of course, quantum computing is also something new, right? So this is pretty amazing. So I hope that you have this insight. Now let's go to another topic. I uploaded the paper already. Take a look. This paper is difficult to read, a lot of theory. So what I'm summarizing is, what I'm trying to summarize is from this paper, right? Because we don't have a good textbook. What is STT-RAM? S is spin, T is transfer, another T is torque, right? You don't know what I'm talking about. But basically, it's related to the spin. And it's something to do with the torque. The torque, you know what is torque, right? How you open the door or whatever. But here is talking about magnetic torque, not a mechanical, but the concept is the same. So we use the spin of the electron to transfer the torque so that you can flip the magnetization of the memory, right? We will learn more, but just at this stage, remember STT is spin transfer torque, okay? RAM with random access memory, nothing special, right? So what is that? I did not give you a picture here, but I'm going to draw. Again, it's very simple as a resistive memory, right? So you see that everything needs to be simple in order to be successful. It has an insulating layer. We call it tunneling layer, right? Insulator. And then you have two other layers. We call it free layer on top. And then what we call, I think we're using reference layer at the bottom. And this two layer, of course, metallic, but more importantly, they are magnetic. Okay, they are magnetic property. So they have a magnetic field, depends on the situation, but it's so simple. Just like resistive memory, we have a top electrode, we have insulator, and then we have a bottom electrode. Bottom electrode usually inert. Top electrode try to release and trap the oxygen, right? So very simple. It has a magnetic layer, right? On the top we call free layer. The middle is insulator, it's called tunnel barrier. When you see insulator, how can insulator be useful? You see it only useful, in the past, insulator can be used as capacitor. Now you see it has two things. One is from resistive memory. You can break it or heal it so that you change the conductivity. From magnetic, and then not just from STT-RAM, from other, you also see that insulator can be used for tunneling. Okay, the bottom layer is a reference layer, right? So based on this name, you already maybe see that information is stored in the free layer. Free layer means what? It's magnetization. You don't need to know what it is, right? It's just like polarization. We don't go into that detail. Magnetization is like polarization is the density of magnetic moment. Remember, polarization, we have dipole moment. Density of dipole moment is polarization. Magnetization is density of magnetic moment. What is that? After all, it's just telling us how the spin, how the magnetic field of your individual atom are pointing. That's it. It doesn't matter, right? We are not going to so deep in this class to do those equations. You just know that, pointing up, north and south, pointing down, south and north. That's it, okay, magnetization. So in this layer, it is used to store information. Then it means it's free. It means that I can flip it, okay? When I write one, all pointing up, north is at the top. When I flip it again, all pointing down, now south is at the top. And then we have a reference layer. We make it stable. Just keep it as it is, right? Why? You will understand later, because we are going to rely on the tunneling current between the free layer and the fixed layer to know what state it is. Okay, so bottom layer fixed magnetization. For example, let's say I make bottom layer always pointing up, right? You can call it north, south, doesn't matter. The free layer can point down or point up, right? Maybe this is 1, and maybe you will call this is 0, this state is 1. That is a memory, right? Any questions about this, about what is a picture of STT-RAM? Now, for any memory, the basic requirement is what? Can you tell me what is the basic requirement for something to be a memory? What can you do?
Can read and write.
Exactly, right? Just like what I wrote here. If you say you have a very good memory, but you can never tell people what you memorize, your memory is useless to me, right? You need to tell me, let me read your memory. How they read, it depends on so-called tunneling magnetoresistance. That is what you just said. Depending on the state of the free layer, the tunneling current will be different, right? I will explain later why, okay? And then how do we write it? The writing is based on STT. So when we write it, we apply a current voltage in different direction. And because of the electron has different spin, it's going to flip the magnetic moment of the free layer. Then we can change it from 0 to 1 or 1 to 0. So the whole physics based on tunneling. You need to have tunneling. You must have tunneling. But how it does is that reading is easy. Just look at the tunneling current. This is called TMR, tunneling magnetoresistance. Another is, yeah, I do tunneling, but in the tunneling process depends on I tunnel from top to bottom or bottom to top. I'm going to flip the free layer. This is called spin top transfer. Okay, we will understand these two mechanism later. Why we want to have STT compared to resistive memory? We also learn PCM. What else did we learn? I think only 2 so far, right? For this novel memory. Ferroelectric, we just discussed in the article of the day, but we don't go into detail, right? It's very fast. It has the speed of SRAM. It has the density of DRAM. Cool, right? Also, this is not destructive. Resistive memory, you keep breaking and healing the oxide, right? You know that if you break something many times, you think that you can always heal it? No, right? But here we're not trying to break something. So almost unlimited endurance. Of course, non-volatile, power consumption is low. Actually, this is the most promising candidate that can replace your SRAM in your CPU because they're fast and also endurance is very good. The only biggest drawback is thermal stability, right? If you make it hot, it can flip. So I think they improve a lot. People are really smart. They through this material engineering. So here I am lying to you. I say this is simple. If you try to look at a real resistive memory that works, it actually have maybe 10 or 20 layers. But you can group them as reference layer and free layer. But why I need 20 layers in the reference layer? This is just to improve all this reliability, thermal stability. That's a very complicated thing. I can admit to you, I don't understand most of those. Okay, so what I'm teaching here is just a simple concept. Okay, so thermal stability is very important. Even a few years ago, maybe 2 to 3 years ago, I asked people, right, what's the drawback? They will always say, you cannot go to 100 degrees C. You will flip. But however, they are good. Now they have product that can go to high temperature. Of course, they compensate this by circuit technique algorithm to avoid all this error, right? But they are inherently worse than other memory in terms of thermal stability. But they can do it. And this is already in production. Okay, this is an overview. Any questions? Now, then definitely we need to just refresh ourselves what is magnetism, right? To learn a little bit so that we will have some idea. I suggest you to go to this website. This website has pretty good systematic discussion of different magnetism. You know what is magnetization, right? You have a magnet, you put to the iron, and then iron will get magnetized. But there are different types. The most important type here that we are using is the so-called ferromagnetism. We also use some anti-ferromagnetism theory in this STT-RAM, right? So you still need to understand a little bit, but just a refresh. We are not going to deep theory. Magnetism, again, is just saying that all these atoms, they align in the same direction, right? North, south, north, south. And you see that this is very similar to polarization. Remember? So I can flip it from pointing north to pointing south. Ferromagnetic material, they have the characteristic of spontaneous magnetization. Do you still remember spontaneous polarization in gallium nitride? Can someone tell me what is spontaneous polarization in gallium nitride? What's the meaning of spontaneous?
Was it the same as relaxed state, or?
Yes, it's related. It means when even it is relaxed, you don't apply any external factor, it is polarized already, right? So spontaneous polarization for gallium nitride, remember, under no strain, just about crystal, I have polarization already because of the symmetry breaking of the crystal, right? You don't need to understand what it is, but basically it is somehow they have a positive and negative charge get separated. And this is spontaneous magnetization. For some material, like iron, it is not magnetized at the room temperature, right? But for some of them, just the magnet itself, at room temperature, it is magnetized already. This is like the spontaneous magnetization. Okay, and the reason is you don't need to go to that deep. Why? They actually energetically, they prefer to be no spontaneous polarization magnetization because that increase their energy. They want it just like if you put a magnet, right, or two compass, north and south, you put it together on two magnets. The north and south, they prefer to be in the opposite direction, right? Think about this. N, S, S, N. This one, they will attract, right? If you put them as N, S, they will repel, correct? Why they will repel? Just because they have higher energy, right? They have higher energy. So they don't want to have magnetization. Magnetization is a higher energy state, right? So maybe this one will make you confused. Oh, how come they want to have spontaneous polarization? And this go to something more quantum mechanical or even quantum electrodynamic that have something called exchange energy. Because I just tell you, don't need to know, just because electron and fermion, they are identical particle. If you try to solve the Schrodinger equation, if you try to exchange, swap the pace of two electrons, you actually will get extra energy. Not because when you swap, you get extra energy, but when you do the calculation in the wave function, you will get a term that will induce extra energy. So actually, they would prefer to be in the same direction to save the energy, right? This is just for you in case you don't understand why they want to point in the same direction, right? So altogether, let's go back to what we learned in primary school. Just two magnets, you know that they want to repel, right? But here, don't worry about that. Just because of the exchange energy in ferromagnetic material, not all material, some of the material are anti-ferromagnetic. They don't want to do that, okay? But anti-ferromagnetic is not, the meaning is not this. It's just saying that you apply an electric field, it doesn't want to align with, you apply external magnetic field, it doesn't want to align with the external magnetic field, right? But anyway, so ferromagnetic means they point in the same direction. So I apply external magnetic field. This is external. What will happen? It's just like polarization. First, if I have a zero magnetic field, right? I start going up, just like polarization. Then eventually you will go to saturation. This is magnetization, right? Each of this is a magnetic moment. Just like now, if you feel confused, try to compare to polarization. Each of these electrons is a magnetic moment. Just like in the polarization, each dipole moment is from negative to positive charge. And then the density of this, let me call this M, density of M is the magnetization. Okay, just like in polarization, the density of dipole moment is the polarization. So you can imagine that when I have very large magnetic field, they will try to align with each other. Eventually, they are all aligned. This is the saturation. This is the saturation magnetization. This is the best you can have because all align, right? You cannot create even more magnetic moment, right? Because they all pointing from south to north. That's it. But now if you reduce the external magnetic field, eventually you will reach here. Even at zero bias, this is called remnant. How to spell? Remnants, right? The remnant magnetic field. So even you remove the external bias, you will get a certain magnetization. And that is how they sell you the magnet. That's my understanding, right? You get a magnet that already have magnetization, right? And you put this in the compass. If you go to the other place, you need to reach so-called coercive, external coercive magnetic field so that you reduce the magnetization to zero. And then you repeat this route. This is called hysteresis route. And you can use this one for the memory. So this is not STT-RAM. This is just talking about ferromagnetism. But this is what you use in hard drive in the past for decades. Okay, and then of course the so-called Curie temperature, right? If you have at very high temperature, you actually will lose your magnetization. Can someone tell me why, based on the physics we have discussed? Why, if I go to high temperature, all this, I cannot feel the magnetization anymore? Just ask yourself, what is magnetization again?
So they're at higher temperature, they're not arranged, they're like random.
Yes, very good, right? Now you align together, then I have magnetization. At higher temperature, they just keep moving. The atoms, they are pointing at different direction. So then they will just demagnetize, right? That's how you, if you get a compass, take the needle, right, or a magnet, heat it up to high temperature, and then cool it down, it demagnetize, everything is gone. Okay, and this one also kind of related to the STT-RAM, right? Your reference layer start with pointing up, while you bring it to Mojave Desert, and then they all demagnetize, then all your stuff are gone. Right, so this is the concept of ferromagnetism. This one just want to briefly touch upon, because when we read this type of material, they will talk about anti-ferromagnetism. Anti-ferromagnetism is just saying that you have two lattice sites. You see that one is pointing in this direction, and other is pointing in this direction. Okay, so they cancel out, right? But they have some special property that can stabilize the STT-RAM, right? Which, again, I don't understand. Okay, so I can only tell you this for now. Any questions? So this is just this is not STT-RAM yet, but let's get into the magnetism world, right? Now our thinking is that, hey, just like dipole moment, I have magnetic moment. They are pointing in different direction. I can align them, then I have a large magnetism. Or I can just make them random, then they have small magnetization, right? And you still have this hysteresis curve, exactly the same as the polarization. Any questions? Now, then what is a STT-RAM? This is the figure that I want to show you. Now I have the drawing. You see it becomes more complicated. The free layer has two stable states, right? With reference to the reference layer. Now you see that, do you see that now? You have more layer. I have the MgO. This is the insulator, what I told you earlier. Okay, and this is the free layer. The whole thing at the bottom is the reference layer. Why it makes it so complicated? Because they want to stabilize the reference layer. Okay, we won't go into the details, right? But first of all, reference layer is changed by referring to the, free layer is changed by referring to the reference layer. So they align in the same direction or opposite. That is how we store the information. Okay, and how do we stabilize the reference layer? Reference layer need to always be referenced, right? If it got flipped, then we get the wrong information. So what we do? We will use so-called anti-ferromagnetic exchange coupling, right? Ignore this. You may see this in the literature, but the main point is you see that we have magnetic sublayer, ruthenium, magnetic sublayer. The whole thing become a so-called synthetic. They are not really anti-ferromagnetic. Like this one, you have two different lattices. But you see, we try to make them in different direction. The overall effect is just like they are anti-ferromagnetic. Okay, but we call it synthetic anti-ferromagnetic because you make it, and they are actually ferromagnetic, but you make it